Hello, students. Welcome back to the next lecture. And now we are going to continue the previous class work on the special relativity, where we have discussed the introduction for the requirement to learn the special relativity, or what was the driving force behind the development of the theory of relativity that we have discussed. And then we have also seen what is the meaning of invariance of physical laws. Invariance means that the equation, the structure of the mathematical equation, will remain unchanged after performing the coordinate transformation. And we have also seen the set of simple coordinate transformation consisted of making a group, and that is known as the Galilean group. It was a 10 parameter group that we have discussed. And especially our interest is to show that the physical law remain invariant. So especially what happens is Newton's laws happens to be so, and therefore we have proved in the last class that upon the coordinate rotation, Newton's law happens to be invariant, form invariant. Okay, that is how we say. And especially for that, you need to know only the rotation matrix. That's all about it. And we have, of course, demonstrated using only one axis of rotation, namely z-axis. So you can, it is quite simple, or you can now visualize what happens if you perform the rotation in the y direction, z direction. So similar expressions will come. Only the rotation matrix will change, but the appearance of the equation will not change. And similarly, you can also perform simultaneously 3 rotations at a time using the so-called Euler angles. So which means that the rotation matrix only will get complicated. So ultimately what happens is whether it is single rotation along one axis or a series of rotation on all the 3 axes, in any situation there will be a rotation matrix. But however, the form of the equation will be preserved. So our conclusion is to say that the rotation, coordinate rotation, will not affect the structure of the Newton's second law, namely that you can retain the same appearance, namely the force vector will be equal to some scalar mass times the acceleration vector. So mathematically speaking, we are talking about vector because it is the property of the vector that is getting transformed. So that is where the interesting point is. That means the conclusion is based on the mathematics. Okay. The coordinate rotation, what it does is the vector is getting transformed. So it is not a physical property, it's a mathematical property. And the mathematical property of the vector keeps the structure of the physical laws intact. That's important. So now that this is the situation, we would like to go further and then look into what happens to the different subject area. So one should not say that only for the mechanics equation the Galilean transformation is valid. Okay, that is not correct. If you carefully remember what we have written as the principle of relativity, we have said that, or we have written that physical laws must remain invariant. That is the point. Physical laws. We didn't say that only mechanics laws. So therefore, it should be very clear that any other subject area, whenever you have an appropriate equation, such equations should remain invariant. So any physical law should remain invariant. So in that scenario, what happens is, historically, after the Newtonian equations, next you have the Maxwell's equation, which is the which happens to be a solid theoretical foundation for the entire electromagnetism. So therefore, our aim today is to understand how the Maxwell's equation will get transformed upon the Galilean transformation. Of course, there is another point to be noted. Yesterday, we have focused our attention only on the rotation of the coordinate axis. Okay, we have translation, we have rotation, and we can also have velocity transformation. Now, out of the 3, translation is quite trivial. It is just moving to another place. So we have not done any mathematics on that. Time translation is also very trivial, that instead of starting the experiment at 9 a.m., you start at 10 a.m. So nothing happens to the equation. So that is also quite trivial. So we didn't write any equation to prove that. But rotation is not that trivial. Without writing down some mathematical expressions, we cannot understand that the equation will remain invariant. So that is why we have done some some exercise, and then we learned that we can in fact prove that the Newton's laws are invariant. Now the question is now clear that after doing the or after learning the rotation as the transformation, what happens next? What happens next means the next type of transformation is the velocity transformation. That means you allow the coordinate system to move with reference to another one. And I already have written down in the last class that when you are moving a coordinate system, we do not know whether it will move with uniform velocity or non-uniform velocity. Anything can happen. So right now we will not make any such condition on the velocity. So the velocity may be uniform, it may not be uniform. Right now we do not know anything about that. So therefore, in this particular condition, we are now planning to proceed further. Let us first understand what is meant by the Galilean transformation. Of course, that's not a difficult thing. So within 5 minutes, you can learn this. And then once you have the Galilean transformation, we can jump into the Newton's equation and then check what happens to the Newton's law under the Galilean transformation. That is what we are going to do. So that will comprise our first half of the lecture. The second half of the lecture will be to focus our attention on the Maxwell's wave equation, Maxwell's electromagnetic wave equation. And then ultimately, after doing the respective mathematics, we are going to ultimately prove that the Maxwell's electromagnetic wave equations are not invariant under the Galilean transformation. So that is the exercise that we are going to do today. So unless you do this, you can't simply agree that just because someone is telling that Galilean transformation is suitable only for Newton's law, whereas for Maxwell equation it doesn't work. If you simply say like that, we can't easily agree and then proceed further. Proceed further means you'll have to proceed to the next equation, namely Lorentz transformation equation. So you always get a doubt, right? When the Galilean transformation equation is available to you, why should I go to the Lorentz transformation equation? So first that question has to be addressed. Only when you have a satisfying answer for that means there should be a compelling reason for you to abandon the Galilean transformation and then go to the Lorentz transformation. You need to have a solid reason for that. And the solid reason is to work out the appropriate mathematical steps. So that's what we are going to do right now. So let me start and then quickly draw the Cartesian coordinate system corresponding to the Galilean transformation. Yeah, so here I'm trying to write down that. Let us first see what is the meaning of the Galilean transformation. For this, we need to draw some coordinate axis. So let me therefore draw a rectangular coordinate system like x and y. So I just want to draw another one so that it has to match with the x-axis. So x-axis has to align. So I am drawing in that gray color line. Okay, so that the visibility will be there when I am drawing the second one. So the second coordinate, that means the moving coordinate, is what I am trying to draw in the green color. So the x-axis of the green color and the x-axis of the white color, they will always align with each other, which means that the coordinate system is going to move along the x-axis only. Okay, you can always move in y, z and combination of that, but corresponding equations will be complicated, and that's why I'm drawing like this. And make sure that the horizontal one is the x-axis, and it doesn't matter what you put it in the vertical and the another axis. I'm talking about the z-axis and the y-axis. Z and y you can interchange, not a problem. But x-axis you have to maintain the same because it is in this direction that the green color coordinate system is going to move. That's what I'm writing. The green color coordinate system is going to move at some speed v. It's going to move at some speed v. I did not say constant velocity. So that's a point to be noted. I am only writing that it is going to move at a speed v in the x direction. As a point. And then now consider any point. I will put it in some kind of yellow color. Consider any point which is represented by xyz. It is also the same point that can be written down as x prime y prime, z prime. Both are equivalent. Okay, equivalent is important. I didn't say equal. The x value and x prime value will not be equal, but the point is same thing. Point means an event. Now, what do you mean by a point? It's a kind of an event. It may be that an airplane is moving there, or that a certain thing is exploding at a particular time. Okay, anything. Now, once this is clear, now directly we can see what is the distance that I am drawing in the white color. So you know whether it is x or x prime, right? It is x prime because it is primed coordinate system. Green color one is the primed coordinate system. Let us now come to the white color coordinate system, which is stationary. So if you are going to measure the same point from the origin, I am now measuring. From the origin, I am now measuring to the same point. Now what should be the distance? Because it is unprimed coordinate system, the distance should be equal to x. That's what I am drawing. So the distance should be equal to x. So once these two are clear, what is left out is the distance between the two coordinates. I'll draw it in yellow color. And now you'll be able to see the distance between the two coordinate system. Let me say s is the separation distance, which is vt. And you understand what is vt. V is the speed of movement and t is the time elapsed. So vt will give you the separation distance. So yes, I am using for separation distance. So the geometry is now clear and quite simple. And once you have this diagram very neatly, you can immediately write down the relation between x and x prime. So let us write down that. I will write down the relation between the unprimed variable and the primed variable. But this relation we are drawing from the diagram. So we are not simply drawing something and writing something. Whatever we write is based on diagram. So the x will be equal to, because that distance you measure, that will be equal to, you see that it is equal to vt plus, and then there is an x prime. So total distance we are going to measure. And that's all. And that is the only equation that you can write down from this particular diagram, because it is only in the x-axis that the coordinate system is moving. Other coordinates, other sides like y direction, z direction is not moving. So there is no special equation to be written down, which means that they are identically same. What I mean to say is they will be identically same. And probably we can say that y equal to y prime and z equal to z prime. So now you have the equations, you have obtained them. And therefore, now regarding time, of course, we didn't write anything about the time. According to the Galilean relativity, t equal to t prime. And you can ask the question why it is so. Okay, you can ask the question on what basis you write t equal to t prime. So I will write down that the reasoning is based on the daily life experience. Okay, so what do you mean by that? So what do you mean by daily life experience is just because you travel, okay, see, just because you travel in a train or you travel in an aircraft, time cannot change. That is an idea. So this is how you feel in daily life, and that is exactly I am writing. Just because you move in a car or an aircraft or in a rocket, whatever it is, time cannot change, and therefore t equal to t prime. So this is the reason, or this is the reasoning given by Galileo, and is also being accepted by Newton, and they all agree upon and say that t equal to t prime. That's it. And so what is the conclusion? Is that this is the conclusion about the Galilean transformation. So Galilean transformation is the simplest one. You got the relations quickly, and remember that this is only for motion along the x-axis only. If you have all the three directions, then you'll have to write down the appropriate expressions for y and z. So whatever I'm highlighting, we will write down separately. Okay, so I would like to write down whatever I am highlighting separately, so that we will do some mathematics with that. So x equal to, let me write down, x equal to x prime plus v times t. The first one. Second one is y equal to y prime. Then we have z equal to z prime. And finally we have t equal to t prime. So maybe, yeah, we can put a box and say that this is the equation. Now what you can do is that if you want to do an inverse calculation, that means the other way, if you want to calculate the other way, then you only have to rearrange the terms. Rearranging the term means, take the take the vt to the left side, then I get x minus vt. And for other equation, nothing to do. You simply write down the other way. And that's it. So this set of equation is known as the inverse Galilean transformation equation. So let us put some kind of a box, and then maybe we can give some number. Let us see. Drawing the vertical line is always difficult. So let us say that this is equation number 1. Anyway, whether you use inverse transformation or that, I don't want to give 1 and 2, etc. But that is the same thing. And now what we are planning to do is this one. Now, how do we know? Okay, how do we know whether the equations are invariant? That's what I'm writing. How to check the invariance of physical laws. Transformation equation is clear. Galilean transformation equation, that is basically a relation between the coordinate system. But how to check the invariance of physical laws? Invariance of the, so for that, let us start with the Newton's law. Okay, that's why A and B always I used to write to say that A means first we start with Newton's law, and then we will go to the Maxwell's equation later. That's what I mean to say. Now, in the one-dimensional situation, you can always write down as fx equal to m into d square x by dt square. You know what is the reason? That our coordinate system is moving only in the x direction. Y and z direction, nothing is moving. So that is why Newton's law also I have written in the x direction alone. Okay, that is what I mean to say. And we will see what happens in the x direction. Okay, let us put some kind of box and say that this is the appearance. Of course, why I am putting a box here is I would like to emphasize that you have to remember the appearance of the equation. It is not that we derived something and putting a box, not like that. The point that I want to tell by saying that this is equation 2 is that remember the appearance, and then we will check whether the same appearance is there at the end or not. Okay, now what we will do? So now apply the Galilean transformation GT. GT is Galilean transformation. What is that? Equation 1 is Galilean transformation, right? So apply equation number 1 to equation number 2. I think you have one, right? Now that is the one. I just want to show you the equation number 1. That is the equation number 1, which is the Galilean transformation. Remember that equation and then apply to equation number 2. So that if you remember and if you have class notes, I don't have to go back and forth in the board. Okay, so let us therefore start with the first derivative, because d square x, the second derivative is there. Let us first evaluate the first derivative, namely dx by dt. So dx by dt, what is that we want to do? Remember, what is that we want to do is time has to go to t prime, x has to go to x prime. That is the idea. So how will you do now? So the idea is first let us finish the time part, dx by dt prime into dt prime by dt. This methodology will enable you to move from time t to time t prime. So the purpose should be clear. T is going to t prime now. So that is the purpose of the chain rule. Of course, the chain rule is simple, but you should know why we are using. I am just explaining. And interestingly, what happens is t equal to t prime. So dt prime by dt is 1, and therefore we can simplify. And fortunately, this is a simple equation. That's 1, right? So I'll write down as dx by dt prime. So now what happened? You see, what happened is time t has been taken over to t prime. That kind of transformation is completed. Okay, and what about the x prime? For that you write down, we know that x equal to x prime plus v times t. So now apply that d by dt of d prime of this expression. You write down that x prime plus vt. So what is this step? This step will take you from the x variable to the x prime variable. That is what we are doing. Okay, let us now simplify. That is equal to dx prime by dt prime plus v times dt by dt prime. Okay, and v is a constant. If you are going to assume like that, then dt by dt prime is 1, right? So because of that reason, it becomes simple now. Dx prime by dt prime plus v. Because that is 1, now we can write it like this. Okay, let us call this by equation number 3. Now let us go to the second derivative. Therefore, second derivative is equal to d by dt of dx by dt. So this is the simplest way you write down. Then afterwards you can apply the chain rule. Now you have to be careful. I am applying chain rule. So that means d by dt prime of dx, that previous expression I am writing. I will show you that the previous expression. Now this is the chain rule. That is what I am trying to explain. So this is the previous expression that I am writing here. That's what I am showing in the blue color cursor. And this is the chain rule part. Okay. And then the last term goes to 1. So that we can now write down that this expression is equal to, what is that expression? That plus dv by dt prime. And that's all. You have a d square x by dt square. So now what happened? X is converted to x prime, t is converted to t prime. That's what we have finished. This is what we mean to say that changing the coordinate system to the moving frame of reference. So to have clarity, I am writing that the left side expression is for the stationary frame of reference, and then the right hand side expression is valid in the moving frame of reference. Okay, now that this board is full, I have to move somewhere else. But remember this equation, or take care of this equation number 4, and I will move to a different place in the board for further discussion. So now that we have done the second derivative is over, right? That's all. I mean, for Newton's law, only 2 derivatives are there. So because we completed, we will write down the conclusion. What I want to tell from this our calculation is like this. In the stationary frame, so what was your equation in stationary frame that you write down? After that, you write down what was your equation in the moving frame of reference. Both let us write down. Fx equal to m times d square x by dt square. That is your stationary frame of reference. What is your latest equation that you obtained in moving frame? That's what you have to write down. That is fx prime equal to mass times the latest equation that you obtained. That's what you have to write down now. D square x prime by dt prime square. Then plus dv by dt prime. That's all. That is the latest equation you got. Now if you compare the stationary frame and moving frame, you see an extra term, isn't it? So now do you agree that the appearance is maintained? Answer is no, it is not maintaining. So that's what I am writing. Now this extra term, if it is there, okay, then we say that it is not invariant. So now we are going to make some conclusion. You have to be careful here. If v happens to be a constant, for example, that is a condition. If condition C, if v is taken to be a constant, then the extra term will go to 0 because time derivative. You see, dv by dt prime, right? So if v is a constant, the derivative of the constant will be 0. Otherwise what will happen? That's what I'm writing. Otherwise, we cannot have the invariance, or we say that the form invariance is lost. Okay, that is the appearance of the Newton's equation is lost. So this is very important conclusion, and we are going to give some terminology. Okay, so now we will make therefore our what is that we are interested to say because of the extra term. I will write here therefore. Okay, so to maintain the form of the equation, we demand that the velocity should be a constant. So now only the condition of demanding comes. That is a place where you have to give your attention. You are going to demand that v has to be a constant. Now only it is clear. Okay, so that is a point to be noted, and therefore we will see in our diagram where was the v. You check out what is the v there. Here is v. You see this v times t. So this v is what we are talking about. Now we demand, after doing the calculation, we now demand that this particular velocity should be a constant. Why we are demanding, you understand, right? Then only the appearance of the Newton law will be preserved. So the green color coordinate system, that means the green color coordinate system must be uniformly moving. It should be in uniform motion. That is the meaning of constant v. Constant velocity means uniform motion. And the technical name that we are going to give is the inertial frame. Okay. So it is not that inertial frame is something you memorize from the school. Oh, we are now giving the name inertial frame. If you don't want to give this name, you can give any other name. But historically, this name has been given. That is the point I am trying to say. Okay. So the name inertial frame is coming from doing some mathematics. That is the point that you have to capture. So let us call such frames as inertial frames. What do you mean by such a frame? Where you demand that the velocity happens to be a constant. So the conclusion is now clear that the Newton's law is going to be invariant. Yes, it is going to be invariant if you agree upon the inertial frame requirement. And that's it over. So we are now happy, and then we will move on to the Maxwell's equation in a new board. I think this board is again full. I'll go to another place and then write down the topic, namely the Maxwell's electromagnetic wave equation. Of course, the Newton's laws, only one x direction is done, but you can always repeat y and z direction, and finally everything will agree upon if the velocity is constant. So that is how you conclude for the 3-dimension. Okay, you have to only know the Maxwell's electromagnetic wave equation for now. Anyway, electrodynamics is there only in the next semester for you, but you don't have to worry about that. Only one equation you need to know, that is this electromagnetic wave equation. The wave equation is quite simple. It is the del square electric field equal to 1 over c square into dou square E by dou t square. So in one dimension, how will you write? So you expand the del square so that I will write down only for the x component, dou square Ex divided by dou x square equal to 1 over c square into dou square Ex divided by dou t square. So this is for one direction. I mean only in the x direction. Y direction, z direction, let us not repeat it. Okay, we can always repeat and verify. Okay, come back to the Galilean transformation, which is x equal to x prime plus v times t. And we have t equal to t prime. Y and z direction I am not writing because anyway there is nothing is changing in y z direction. That's the point. Now you see the x has to be changed and the t has to be changed. So x and t are visible in the Maxwell's equation. We want to change. So how will you do that? Let us apply the Galilean transformation to the equation number 1. So I will write down like this: x prime equal to take the vt to the left side and then x minus vt, and we have a t prime equal to t. So now a little bit of partial derivative we'll have to evaluate. That's why I'm writing in a proper way with some equation number 2. Okay. So what is our understanding is that x prime is a function. This is important. This is very important. X prime is a function of, that is what is the meaning. That statement that what I am writing, you have to read like this: x prime is a function of, like that you have to read. It's a function of what? It's a function of x and t. How do you know that? Means you have to see the equation number 2. Okay, this is what is visible from your Galilean transformation equation. Or equivalently, if you want to write in an inverse transformation, you can write down like this. You can use the inverse Galilean transformation and say that x is a function of x prime and t prime. So whether you write that way or this way, they are equivalently same. So I will say that this is equation number 3. And this is for the x. And similarly, you can also write for the time t is a function of x prime and t prime. This expression for the time I will come for later, but let us first concentrate on the x. Okay. So equation number 3 is very important. Equation number 3 tells you that x is a function of x prime and t prime. Therefore, let us start with the equation number 3 and then apply the equation number 2. So let us first write down how to evaluate some of the partial derivatives. So these are simple partial derivatives. So let me first finish this. Dou x prime by dou x is 1. Dou x prime by dou t equal to minus v. All these things are visible, right? Dou x prime by dou t is minus v. You follow the blue color cursor. Okay, one more partial derivative you can write down: dou t prime by dou x. How much is that? 0. There is no x, right? So 0. And we can also write one more partial derivative: dou t prime by dou t. So t equal to t prime means what? 1. So we have a set of partial derivatives. Let us call by equation number 4. And now we are ready. Now we are ready to use the equation number 3. So let me put some separation, otherwise it will disturb. And now let us take equation number 3. So I will say that from equation number 3, what we can do? We are going to perform some partial derivatives. So what we can write from the equation number 3 is that dou by dou x equal to, because x is a function, you see that you have to see x is a function of x prime and t prime. That's what it is. So it is a function of two variables. So you have to add two terms. So dou by dou x prime by dou x plus. What about the second term? Second term is t prime. Therefore, it is dou by dou t prime by dou x. So you see x here, x there. So in all the denominator you should have x. And that is the meaning of the partial derivative. So and now we can simplify. Let us see what can be simplified. I will put a circle there that can be simplified from 4. Now you can see that that is a 1 is there, right? From where it is? It is equation number 4. And similarly, that particular circle, I will put the last term. How much is that expression? Is 0. Isn't it? So 0 is visible, right? And if you are going to do that substitution, we will be getting dou by dou x is dou by dou x prime. This is the first partial derivative, first order derivative for space. And what will happen in 3 dimension? In 3 dimension, dou by dou x, dou by dou z will become a gradient operator. So gradient operator in the moving coordinate system, gradient operator in the stationary coordinate system, they are identical. That is the conclusion. So let me write down equation number 5. Of course, I am not changing equation number because it's the same thing, right? 1D or 3D, that's all about it. So coming to the space part, this is over. I want to tell you clearly that the prime notation means, let me write down that the prime notation means moving frame of reference. That's what I want to tell. You always remember, whenever prime comes, we are talking about moving frame of reference. If there is no prime, unprimed means stationary frame of reference. So if you remember this kind of symbol, then we can understand the equation and proceed further. Now that we completed the situation for the space derivative, we can move ahead to calculate the time derivative. I'll write down. Let us try the evaluation of time derivatives. It is in somewhat green color. I will change the color to the white. So what do you have for the time? Similarly, we have the expression time is a function of t is a function of x prime and t prime. So I will write t prime first and x prime. It doesn't matter. Both are same. Okay. We are going to do addition, right? So 1 plus 2 or 2 plus 1 both are same. So okay. So what is dou by dou t? Dou by dou t prime by dou t. Dou t prime by dou t. Yeah, that's correct. And then go to the second term. Second term is dou by dou x prime by dou t. So t should be, you have to see the t, everywhere t should be there. Otherwise you have made a mistake. Okay. So it is very clear that x prime and t prime will be there. So this is how you will have to write down the partial derivative. Because it is a function of two variables, we will be having only two terms in the final expression. Okay. Now, as usual, see the equation number 4 and then simplify. So if you are going to use the equation number 4, we can simplify some of the expressions. So let us use the equation number 4. So therefore, we have dou by dou t is equal to dou by dou t prime into 1, because that is 1 here, then plus. Then that expression is dou by dou x prime into minus v. So minus v is coming from equation number 4. Now you simplify. Dou by dou t is given by, therefore it is dou by dou t prime. Now you get a minus velocity v into, then dou by dou x prime. That's all. That is the only simplification we can make. And let us call this as some equation number. Now you have the first order time derivative. That also you make a note. And remember that, okay, previous one is 5. So let us give 6. The Maxwell equation is a second order differential equation in space and time. Okay, so that point we have to do. Now suppose if you move to the three-dimensional situation, how this equation will look like. Dou by dou t equal to dou by dou t prime minus v will become v vector. Then it becomes a dot product with a del operator, because you know the del operator, dou by dou x. So that is how the equation will look like in the case of the three dimension. And anyway, we have not made any change, so I don't want to change the equation number. We will maintain the same equation number 6 even for this. Now that we completed, right, now that we completed first order partial derivative, we are ready to move to the second order time derivative. Okay, so we will write down, but for the Maxwell equation, I'll write down, but for the Maxwell equation, we need second order time derivatives. Which means what? You have to do one more differentiation. That's all about it. So let us see that how to do. So you start with the equation number 6. No, that is the first derivative. No, so take the equation number 6 and differentiate once. That is the meaning. So we can write the following, that dou square. So I want to write down that the second order partial derivative dou square by dou t square will be equal to now I am applying the chain rule. Remember this, I am applying the chain rule. So dou by dou t prime of, because of chain rule I am putting t prime, okay, of that whatever expression you got now. So I am copying that, minus v into dou by dou x prime. Just now you got, right, equation 6, that is this one. Then chain rule is there, so you have to multiply dou t prime by dou t. Plus, similarly, you have to repeat it for the dou x prime. So dou x prime, the same idea. Copy whatever you got it in the equation number 6. And then because of the chain rule, multiply by dou x prime by dou t. But just to verify equation number 6 is copied correctly or not. So let me go above. Yeah, whatever is there in equation number 6, that should be there now. Please verify the blue color cursor. So that term which I am now showing, that should be copied here. Not only there, there also you have to copy, 2 places. So that's all. If you do that, that means we are performing the one more derivative. Okay, once this is clear, now you know how to simplify. For simplifying, you'll have to use the equation number 4. So what happens to the sum of the terms? This term goes to 1. This is equal to 1. And there is one more term, the last term. That last term will be equal to minus v. Okay, the last term is equal to minus v. So if you put them and then simplify, let me erase this equal to. That space is not enough. So if you are going to simplify, let us simplify. What is dou by dou t prime of dou by dou t prime? It is second order derivative, right? That's what I'm writing. Dou square by dou t prime square. That's all. Only one term is there. Then afterwards, you now search for space terms. So space term, if you search now, you have a minus v, so that must become a plus. Then v square. Then it must be dou square by dou x prime square. I think there is a dou x prime, so it is correct, dou x prime square. Then I don't know, plus or minus, there is a minus here. And then you have a minus v. 2 similar terms are there, so I'll write down 2v. Then there is a dou square, but the denominator is not common, right? So one is dou t and one is dou x. So dou square by dou x prime dou t prime. Like that it will come. And that's all. I think no more, all the terms are taken care. So which means that we have completed the evaluation of second order partial derivative. So first order partial derivative is, first order partial derivative is there here for the space. Now what we have to do is second order partial derivative should be done for the space. I will write down that. But this is not difficult, so directly I will write down first line that del square will be equal to del prime square. You know why it is, no? It is there, no? Equation number 5. Del equal to del prime means del square equal to del prime square. That's all. So there is nothing to do much. So we are getting, at least for space derivative, it is easy. Our life is easy. So equation number 8 is coming due to equation number 5. Okay. Now we are ready to go to the Maxwell equation. So remember the Maxwell equation. I want to write the Maxwell equation, which is equation number 1. And then we have to use equation number 8. I am putting a tick mark so that we need them now. In addition to equation number 8, we also want equation 7. So I am putting tick there. Okay, so these are the equations we need. So I will write down that we are going to use equation number 7 and 8 in the Maxwell's equation 1. So if you are going to use that, what will happen? So let us first write down that the del square E equal to 1 over c square into dou square E by dou t square. That was the equation number 1. And now we are interested to simply transform to the primed coordinate. So what is del operator square? It is equal to del prime. That's what I'm writing. So del equal to del prime. So we are happy in that way. And then coming to the right hand side is a trouble. That big expression we have to write down now. Okay, dou square by dou t square. So whatever is there in equation number 7, you have to copy it. Then the second term v square dou square e prime divided by that is x prime, so dou x prime square minus 2v. Then we have a dou square e prime divided by this is dou x prime dou t prime. You understand why E prime is written, right? Electric field will go to electric field prime in the moving frame of reference. That is why prime is attached to the E also. Okay. We have completed our calculations and we are going to write down the conclusion. So what is the conclusion means? From where will you get? From the latest equation, that is from 1 and 9. Equation 1 is stationary frame of reference. Equation 9 is moving frame of reference. You compare them and then tell what is your conclusion. Whether the appearance of the Maxwell equation is original appearance is retained or whether the original appearance is lost. That is what you have to tell. So it is very obvious and very clear that the form of the Maxwell equation is lost. So instead of saying that the form of the Maxwell equation is lost, we say that the Maxwell's equations are not invariant. So slightly technical term, that's why we prefer this terminology. Maxwell's equations are not invariant under the Galilean transformation. So as you can see that why it is not invariant, we have extra terms are there, isn't it? So I'll show some extra terms in the green color. 3 terms are there, no, right? And so the last 2 terms are the one which is giving trouble. So those 2 terms are the extra terms which is responsible for spoiling the invariance of the Maxwell's equation. So that particular term, extra term, I will encircle them. Only first term I am putting tick, which is all present. Okay, so those things are good. The only thing is that this particular 2 terms which I am enclosing in some kind of round encircling, so that is the one that gives you extra terms, and that is the one which gives you trouble in the sense that they are responsible for spoiling the invariance of the Maxwell's equation. Okay, that's the conclusion. That's okay. That's okay. Then so what can be done then? If it is the case, what next? So you understand the point that the Newtonian equations are invariant. Okay, it's very good. Maxwell's equations are not invariant. So what next? What can be done in this scenario? Okay, so I would like to address this in the next class.